Hi everyone, welcome to Huck Circuits. Today we're looking at the simplest circuit, a voltage source and a single resistor. We're starting with this circuit because it's very fundamental to all of circuit analysis. The principles that we solve as we work through the problem, you'll see it over and over again in more complex circuits. So as we're starting, the first thing we want to know is the formula, which is voltage equals current times resistance. That's the formula. If you see a circuit like this and you want to know what the current is, which is going in this direction, the current comes out of the positive terminal. The positive terminal is right here, the positive terminal of the battery. It comes out from this side, goes around this way and into the negative side right here, and it goes like that over and over again, forever and ever. It just keeps going until the battery finally dies out, and that's what's happening there. So when we're doing that, we know that we have the voltage, which is voltage equals 5 volts, and our resistor R1 equals 1 kilo ohm, which is 1,000 ohms. Now we want to find the current. So we have our equation, and to solve, we'll do I equals V over R. It's just pretty much manipulating Ohm's law right here. Ohm's law is right there. If we manipulated that, and let's keep going. So if we start plugging in the values, we'll get 5 volts over 1 kilo ohm, which we could rewrite as just 5 over 1,000. Now let's go ahead and solve this. So we have 5 divided by 1. Now one cool thing about this calculator is that you can pretty much choose K here for 1K, and it gives you the value of 0.005 amps. Okay, so we got our number in amps, but we want to get rid of all the zeros and just kind of clean it up. So if we just multiply that, or let me hit equals, we just multiply that by 1,000. Now we got, or equivalently, it's 5 milliamps. So these are our answers right here. So, and we discussed already that the current is coming out and going this way. So with that knowledge, we can say that the current, which is traveling this way, I equals 5 milliamps. Okay, so we're doing good so far. We got a current. Now, after we get the current, we want to make sure that this circuit system, this drawing right here, all of it, it's a system. And we want to make sure that the energy that is being used up is the same as the energy that's being supplied. And energy over time is power. That's kind of where we're going here. So we want to know the power across this resistor. Now there's a formula for that also. The formula is P equals I squared R. Now that means power equals the current. You square the current and you multiply that by the resistor. So that is the formula that you use anytime you see a resistor. You'll always use this formula right here. So let's plug in our values now. So power equals, we'll use the amps for the current and not the milliamps. So 0.005 squared times 1,000. Okay, let me just erase that one. Okay, 1,000. And let's see what that gives us. Square that times. Okay, so we got 0.025 watts. What does that mean? If we got this value right here, let me just, right there, 0.025 watts. So that means that going through this resistor, we're using up energy. As the current goes through this resistor, the energy is being used up because power is energy over time. So energy over time, time being in seconds. So every second, energy is being used up. Exactly how much energy? Well, you're using up 0.025 watts of energy every second going through this. Watts is also basically it's joules per second, where joules is a unit for energy. So now we know how much energy we're using up every second, or how many watts we're using. We want to make sure that this system is balanced. We want to make sure that the energy that is being used up here is the same energy that is being supplied by the source, which is right here. And there happens to be a formula for that also, which is power. This is for the voltage source now. I guess for this power here, I'll say power for R1. But this power for the voltage source is negative V times I. So power is the negative sign times the voltage source times the current. So I guess the thing that sticks out here is right here, that negative sign. Where is that negative sign coming from? Like, why is it there? So the answer to that is this. Let's scroll down a little bit here. So usually, let's say you have 2 points here. You got a resistor. So when current is traveling, when current I travels this way, and it's going through a resistor right here, you can think of the resistor as so when you see a resistor, you can kind of think of it as a current to voltage, a current to voltage converter. What that means is this. What that means is when current travels through the resistor, you get a voltage drop. That's the key word, voltage drop. I'll even write that down because it's a very important term that comes up all the time in circuit analysis. Voltage drop. So you get this voltage drop here through the resistor. So there's actually a voltage going this way. And resistors, they always go from their voltage drop from positive to negative. That's actually why we use that I square R, which is C up there. So the current, you could have positive current, when it goes from positive to negative. If negative just travels the opposite way, in terms of the conventions that you set up, you could have negative current. Negative current doesn't mean this, like, negative current is still current. Negative just means that the current is traveling in the opposite direction. So if this way is positive current, that means negative current is this way. It just flips it, the negative sign flips the direction. So now that we know that, we can see that instead of using a resistor, let's just say, let's draw like a blob. It could be whatever. And this blob, we can say has like a voltage drop also across it. So you got a plus and a minus, and right here there could be a voltage drop. Now this blob actually is some sort of circuit symbol. It could be a resistor, or it could be a capacitor, or it could be an inductor. So a resistor or a capacitor. So that's just what that circle represents. So anyway, why are we going through this discussion? We're going back to here, right here. The P equals negative VI. We're talking about the negative sign. So as it turns out, when you have like a source, let's get that voltage source right here. Okay, yeah, so we got this voltage source right here, right there. So current is going this way. When current travels through this right here, you can see that the current goes from negative to positive this way. So anytime current goes from a negative to a positive, that's like a voltage drop also, but it's a negative voltage drop, which is where this negative sign comes from. So you got a negative voltage drop right there. So now that we know that where that negative comes from, let's go ahead and continue solving this this equation here. So you got a negative, and the voltage is 5 volts. 5 volts, and the current is 0.005 amps. So let's see, once we do those calculations, times 0.005. So we got the answer here to be negative 0.025 watts. That's the answer here. So let's take a look. So the power through the resistor was 0.025 watts positive, and the power through the source is negative 0.025 watts. They're both the same magnitude, but they're opposite in sign, and that's what you want to see. That means that we have a system where the energy in equals the energy out, and that is the solution to finding how much current is going through the resistor and how much power is being dissipated through the resistor as well. Thank you for tuning into Huck Circuits, and please stay tuned for more videos like this on the way, as well as covering embedded systems and anything pertaining to electrical engineering. Thank you.